Hello everyone, welcome to my presentation. My name is C.Tze Ng from the University of Sheffield, UK. In this presentation, I'm going to talk about the static assessment of notched additively manufactured ABS polymer. Before I start my presentation, I would like to thank my supervisor, Professor Susmel, and the university's SURE scheme for supporting me throughout the completion of this research project. So, without further ado, let's get started. So, the outline of this presentation is as follows. I will start off with the context and aims of the project. Then, moving on to the geometries of AM-ABS specimens, as well as showing the manufacturing parameters. Then, I will explain the testing details, discussing the results, and cracking behavior of the specimens. Next, I will briefly discuss the fundamentals of the theory of critical distances (TCD). Also, I will discuss the calibration of critical distance and assessing the accuracy of TCD. Finally, I will summarize my presentation in the conclusion section. We know that additive manufacturing techniques has gained its popularity over the years. One of the key advantages of additive manufacturing is that it is able to manufacture structurally intricate geometries at a relatively higher accuracy, shorter amount of time, and lower cost. However, from a structural integrity point of view, this feature is of concern, as the side effect of these complex geometrical situations is that it will lead to the localized stress concentration phenomena, which is sometimes a detrimental effect on the static strength of such additively manufactured components. Hence, it is essential for engineers to accurately perform static assessment of AM components containing these geometrical features. Therefore, theoretical tools that are able to predict static strength of AM components accurately, rapidly, and economically become invaluable to practitioners. Therefore, directly showing the importance or significance of this research, which is to validate the accuracy and robustness of TCD. The ultimate aim of this project is to contribute to the knowledge gap of stress concentration effects on additively manufactured engineering components containing intricate geometrical features, whereas directly this project aims to assess the accuracy of theory of critical distances (TCD) in estimating static strength of notched AM-ABS components. Besides, it also aims to investigate the effects of manufacturing angle on the static strength of notched ABS specimens. So some of you may ask, why do we introduce notches in our experiment? The reason is that it is to simulate the localized stress concentration phenomena by introducing notches on the AM components. Note that the static assessment tool that we are referring here is TCD. The configuration of additively manufactured ABS specimens are as shown in the figures. Figure A shows the geometry of the dog bone plane specimen, whereas Figure B shows the geometry of compact tension CT specimens. Figure C to E shows the specimens with U notches under tensile test at a notch radius of 0.5 mm, 1 mm, and 3 mm. Figure F to H shows the geometry of specimens with U notches under 3-point bending test. Similarly, figure I to K shows the geometry of specimens with open notches under tension, which has a notch radius of 0.5 mm, 1 mm, and 3 mm at a notch angle of 135 degrees. Lastly, the figure L to N shows the geometry of specimens with open notches under 3-point bending test. The manufacturing parameters of additively manufactured ABS specimens are as follows. The specimens are printed using the fused filament fabrication-based 3D printer. The model of the 3D printer is the Ultimaker 2 Extended Plus. The filament used are Prima 750 ABS and they are gray in color. The diameter of filament is 2.85 millimeters, diameter of nozzle 0.4 millimeters, nozzle temperature at 255 degrees Celsius, build plate temperature at 90 degrees Celsius, and the printing rate of 30 millimeters per second. The infill density of the specimens is set at 100%. The height of each layer is 0.1 millimeter, whereas the shell thickness is set to 0.4 millimeter. The specimens are manufactured flat on the build plate as shown in the diagram. The manufacturing angle for plain specimens are set at 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, whereas the manufacturing angle for notched specimens is set at 0 degrees, 30 degrees, and 45 degrees. The material layout and the corresponding manufacturing angle is shown in the diagram on the right. Next, moving on to the testing details. The tensile tests are carried out on plain, notched, and CT specimens. An extensometer with gauge length of 50 mm is used for tensile tests of plain specimens. For 3-point bending test, the span between lower supports for open notches is set at 60 mm, whereas the span between lower supports for U notches is set at 50 mm. All tests are carried out by the Shimadzu universal machine at a displacement rate of 2 mm per minute and a frequency of 10 Hz. Now we shall discuss the results of plain specimen. Figure A shows the Young's modulus recorded at different manufacturing angle, whereas Figure B shows the ultimate tensile strength. Figure C shows the 0.1% proof stress. The average values for the said mechanical properties are circled in red, as shown in the diagram. The assumptions that we made from the results of the plain specimens are as follows. Since the mechanical properties are all within 2 standard deviation of mean, the influence of material layout on the said mechanical properties is assumed to be insignificant. Note that the notched AMABS specimens are only manufactured at 0 degrees, 30 degrees, and 45 degrees. This is because the mechanical properties of AMABS manufactured at 0 degrees and 30 degrees are comparable to the ones manufactured at 60 degrees and 90 degrees from the results of plain specimens. From the results of notched specimens under tension and bending as shown in the figures A to D, it is observed that under both tension and bending, breakage occurs when applied force or moment has reached the maximum value. It is worth noting that the AMABS have a low notch sensitivity. Under tension, there are 2 different slopes as shown in the force versus displacement curve. This phenomena occurs regardless of sharpness and profile of the notches. A plausible explanation to this case is that slope 1 may be governed by the relative displacement between adjacent filaments, which is a sliding-based mechanism, whereas slope 2 is governed by tensile properties of individual filaments. However, this still requires further investigation. Under bending, it is always observed that the non-linear behavior always occurs at the start of the testing, which could be explained by the rig's mechanical adjustment. Moving on to the cracking behavior of the specimens. The cracking behavior of plain and notched specimens are very similar. The crack initiation is governed by mode 1 stress, whereas the crack length is always approaching to the shell thickness. Under crack propagation phase, it is observed that a zigzag path is shown and can be summarized into three failure mechanisms, which are the debonding between adjacent filaments, debonding between adjacent layers, and the rectilinear cracking of extruded filaments. For CT specimens, the crack initiation is slightly away from the notch tip. This could be due to the deposition method of the material near the sharp notch. The crack propagation is purely under mode 1 failure. This is because its manufacturing angle is at 45 degrees. Fundamentals of Theory of Critical Distances (TCD) is as shown from figure B to D. There are mainly three formalizations of Theory of Critical Distances, which are point method, line method, and area method. The mathematical definitions are shown accordingly as well. For point method, the effective stress defined to be equal to the linear elastic stress at a distance from notch tip equaling to L/2. For the line method, the effective stress can be obtained by averaging the linear elastic stress along the notch bisector over a distance equaling to 2L. Finally, for the area method, the effective stress is determined by averaging the linear elastic stress over a semicircle that is centered at the notch tip and has a radius equaling to L. So, it is assumed that the effective stress is less than or equal to the ultimate tensile strength. The notched AM-ABS specimens is assumed not to break. The calibration of critical distance L for application of TCD is as shown as follows. It is assumed that additively manufactured ABS can be modeled as homogeneous and isotropic material. It is also assumed that the additively manufactured ABS can be modeled as a linear, elastic, and brittle material. The function to calculate critical distance is as shown below. The critical distance is calculated via the average plane strain fracture toughness, which is obtained from the tensile testing of CT specimens. It is also calculated via the average ultimate tensile strength from the tensile test of plane specimens. The calculated critical distance is 4.1 millimeters. Due to the fact that the integration length 2L is equal to 8.2 millimeters, which is larger than half of the net width of the specimens, the line method cannot be applied in this scenario. The accuracy of the theory of critical distances (TCD) is as shown in the graphs below. For both point method and area method, it is observed that the error interval of the results mainly fall between 20% of the error interval. The error calculation is calculated based on the formula as shown. This therefore validates the accuracy of TCD as a static assessment tool for the additive manufactured ABS components. There are four main points for the conclusion. The first main point is the influence of manufacturing angle on relevant mechanical properties of additively manufactured ABS is actually small. This is because all relevant mechanical properties are within 2 standard deviations of the mean, as the manufacturing angle varies in the range of 0 degrees to 90 degrees. It is also observed that an increase in the notch sharpness does not always lead to a decrease in the static strength of AM-ABS, as it has a low notch sensitivity. It is also worth noting that the propagation of cracks fully depends on the material layout. Finally, the theory of critical distances is proven to be a valid and accurate static assessment tool for the AM-ABS engineering components. That's all from me, and thank you for your attention.